In the last video, we saw that none of the three voting systems that we've studied, plurality, board account, and plurality with elimination, that none of those three satisfy the Condorcet condition. That is to say that in each of those three methods, it's possible to have an election in which there is a Condorcet candidate, but that the Condorcet candidate does not win. Remember that a Condorcet candidate is one that would beat any of the other candidates head-to-head. In this video, we'll study another voting system that does satisfy the Condorcet condition, and it's called a pairwise comparison system, also known as Copeland's method. The idea is somewhat simple. We start by comparing each pair of candidates head-to-head, and then we declare as the winner the candidate who has the most head-to-head wins. This method gets its name because we can also call a head-to-head comparison a pairwise comparison. Pairwise because it's just between two candidates. Let's return to an example we've looked at before. The 2009 Burlington, Vermont mayoral election. Once again, here is the preference schedule from that election. Remember that in an earlier video we did some head-to-head comparisons for this election. This time we're going to do all possible head-to-head comparisons. So in this election there are four candidates, K, M, S, and W, and what I'm going to do now is write down all possible pairs of two candidates among the four. So we have K and M, we have K and S, and we have K and W. So I've matched up K with each of the other three candidates, but I still need to find pairs within the remaining three candidates. For example, we have M and S, we have M and W. By the way, notice I'm not writing M and K again because we already had K and M. The order is not important. And the last pair is S and W. So I'm not going to go through all of these in detail, but let me remind you of what I mean by a head-to-head matchup. Focusing on the first matchup, K versus M, I'm going to highlight all of the columns where K is ahead in yellow. So these are columns corresponding to voters who ranked K above M. And tallying these up, we get 3,908 votes where K was ranked above M. And now I'll highlight the remaining columns in blue. These are ones corresponding to voters who ranked M ahead of K. Tallying these up, we get 5,068 voters who ranked M ahead of K. So this was one possible head-to-head matchup, the matchup between K and M, and we can see that in this case, M wins the head-to-head matchup. I won't go through the other calculations in detail, but here are the results. And you can see I've circled the winners. So remember, in our voting system, we're supposed to see who has the most head-to-head wins. So let me go ahead and count the number of head-to-head wins for each of the four candidates. So counting up the wins, we see that K had 2 wins against S and W, M had 3 wins, S had no wins, and W had 1 win. So since M had the most wins, M is the winner in the pairwise comparison voting system. In fact, as we'd seen in an earlier video, M won all 3 of their pairwise comparisons, and that makes M the Condorcet candidate for this election. Indeed, in any election in which there is a Condorcet candidate, that candidate will win all of their head-to-head comparisons, earning the maximum number of head-to-head wins, and dealing each of the other candidates a loss. Therefore, this voting system will definitely choose the Condorcet candidate as the winner if there is a Condorcet candidate. And that's exactly what it means to satisfy the Condorcet condition. And so it's a fact, or rather a mathematical theorem, that the pairwise comparison system satisfies the Condorcet condition. Okay, let's look at another example. So here we have 3 candidates, A, B, and C. So I'm about to write down all possible head-to-head matchups between these 3 candidates. So we have A versus B, A versus C, and B versus C. Again, I'm being careful not to double up my head-to-head matchups here. I don't want to include both A versus B and B versus A, for example. So going through the first head-to-head matchup, that first column has A ranked above B, so I'll highlight it in green for candidate A. The next two columns have B ranked above A, so I'll highlight them in blue for candidate B. The next column has A above B, and the last column has B above A. Tallying these up, A gets 11 and B gets 13. So B wins that head-to-head matchup. Now let's look at the next matchup, A versus C. In each of the first two columns, A is ranked above C, so I'll highlight those in green. And in all of the last three columns, C is ranked above A, so I'll highlight those in red. Adding these up, we see that A and C each have 12 votes. I'll talk about how to deal with that in a moment. Finally, we'll look at B versus C. In the first column, C is ranked above B, so I'll highlight that in red. The next two, B is ranked above C, so I'll highlight those in blue. And in the last two columns, C is ranked above B, so I'll highlight those in red. So B gets 5 votes, and C gets 19 head-to-head. So now let's tally up the number of head-to-head wins for each of the three candidates. So candidate A had 1 loss and 1 tie, but the way we're going to do this is say that ties count as half a point. And so I'll record that A got half a win. Candidate B got 1 win and 1 loss, so it gets 1 point, and C gets 1.5 points for 1 win and 1 tie. So C has the most wins, and so C wins overall. I also want you to notice that in this example, no candidate beat all of the others. C tied one of the candidates. So C was not a Condorcet candidate. There was no Condorcet candidate. However, the method still works. In the last 2 videos for this section, we're going to focus on the properties that these voting systems do or do not have. Properties like the Condorcet condition. However, before we do, I want to bring up one more interesting point here about the pairwise comparison system. If you're using this system, you might wonder, how many comparisons am I going to have to do? So I'll ask the question, when there are an arbitrary number of candidates, let's say n candidates in the race, how many pairwise comparisons are there? Well, this is the number of pairs within the n candidates. So mathematicians call this n choose 2. You start with n candidates, and we're choosing exactly 2 of them. And we're interested in the number of possible ways to do this. The mathematical notation for this is n and 2, written in parentheses like this. So this is the number of choices of 2 candidates among the n possibilities. So before I do this in general, let me talk through a couple of cases that we can figure out right away. If there are only 2 candidates, there's only one head-to-head comparison. So I'll write that as 2 choose 2 equals 1. We also saw in the last example that when there were 3 candidates, A, B, and C, I had 3 comparisons to do. A versus B, A versus C, and B versus C. So I'll write that as 3 choose 2 equals 3. Finally, in the Burlington, Vermont example, the first example we did, there were 4 candidates, and I ended up doing 6 pairwise comparisons. And so I'll write that 4 choose 2 equals 6. So now we wonder, what's the general pattern? So if there are an arbitrary number of candidates, let me give those candidates name. I'll call them candidates A1, A2, A3, up through AN. So now let me try listing all of the possible pairwise comparisons. I could do A1 versus A2, and do A1 versus A3, and so far all the way down to A1 versus AN. So you can see I'm trying to be systematic here and doing all of the pairs that involve A1 first. Now I can focus on pairs that don't involve A1. Before I do though, let me note that I've done n-1 comparisons at this point. It's n-1 because I've compared A to all of the other candidates, all the candidates other than A1 that are left. Next, I'll compare A2 to all of the candidates that come after A2. So A2 versus A3, A2 versus A4, all the way down to A2 versus AN. So now I've compared A2 to all candidates other than A1 and A2, so that adds up to n minus 2 comparisons here. And I'll sort of proceed in this way, and the very last comparison would be between a n minus 1 and a n. And so you can maybe start to see the pattern. If I tally up all of these comparisons, I'm adding up all of the numbers, n minus 1 plus n minus 2 plus n minus 3, all the way down to 1. So if I'm trying to figure out what n choose 2 is, well, it's n minus 1 plus n minus 2 plus n minus 3, all the way down to plus 1. I'm adding up all of the integers from 1 to n minus 1, and that will total to n choose 2. That is to say, n choose 2 is the sum of the integers from 1 to n minus 1. So this gives us a way of calculating how many pairwise comparisons there are for n candidates. If there are 4 candidates, we need to add up all of the numbers from 1 to 4 minus 1, so 1 plus 2 plus 3. And in fact, that gives us exactly the answer we had up here, 1 plus 2 plus 3 equals 6. But in fact, we can do even better. There's sort of a shortcut for adding up all of the integers from 1 to n minus 1. And the shortcut arises from changing the order in which the numbers are added up. So let me write this out. 1 plus 2 plus up through, and I'm just going to write the first half of the numbers. So I'm not going to write all the way up to n minus 1. I'm just going to go up to n minus 1 over 2. And let me write the rest of them. We're trying to go up to n minus 1, so let me write the next number as n minus 1 over 2 plus 1. And now I'm going to kind of write them backwards. And the last two numbers to add up are n minus 2 and n minus 1. So what I've done is I've added up all of the numbers from 1 to n minus 7, but I've just sort of written them in a weird order. But here's the clever part. I'm going to add up these one column at a time. So when I add up the first column, I get exactly n. When I add up the second column, I also get exactly n. And in fact, for all of these columns, when I add each column up, I get exactly n. So I'm adding up n a bunch of times here. Well, how many times did I write it down? Well, I wrote it down n minus 1 over 2 times. So this ends up equaling n minus 1 over 2 times n. Now you might have noticed I was a little bit sneaky here. This method might not work if n is an odd number, but it turns out the formula that you end up with in the end is still correct. To see an example, let's say I wanted to add up all of the numbers from 1 to 100. Well, let me go ahead and add them in this clever order and add 1, 2, 3 up through halfway, which is 50. And now I'm going to write the rest of them sort of backwards in the next row. So 51, and I'll go backwards. And the last few are 98, 99, and 100. And now we add up each column one at a time. So the first column adds up to 101. So does the next column. So does the next column. And all of the columns are going to add up to 101. So does the last column. And how many columns are there? Well, there were 50 columns, so this is going to be 101 times 50. So the upshot of all of this is that the number of pairwise comparisons for n candidates is equal to this number that mathematicians call n choose 2, which we write this way. That ends up being equal to 1 plus 2 plus 3 up through n minus 1. And even for that, we have a shortcut for figuring it out, which is just n times n minus 1 over 2.